Okay, so good morning or good afternoon, everyone. My name is Momin, and today I'll be talking about the online Matroid secretary problem. A couple of keywords in there that will uh, dive in a moment. So, actually, this presentation is sort of a joint presentation. So, in this one, I will introduce what the Matroid secretary problem is. What that means is first I will introduce the classic secretary problem, and then we'll see what Matroids are, and then some examples to give you some intuition. And after that, my colleague Daniel will give choose a specific Matroid class, and then show a simple algorithm for it. Okay, so the online secretary problem is a classic problem in online algorithms and optimal stopping theory. It was first proposed by Merrill Flood, and it gained traction after his 1960s paper. To tell you the basic story, you can assume, for example, you apply to 10 internships, and those internships start giving you some offer, but in their own time. So, and whenever you receive an offer, you put a value to it. You check out the pay, you check out other benefits, and you assign a high value if you really like the offer. But more crucially, you have to either accept or reject the offer then and there, or within the specific time limit. So to really formalize it, there are n elements that arrive in an online manner. What that means is that we don't know their weights beforehand, and it is only revealed to us when the element arrives. Secondly, the order is uniformly random, so we don't even know which order it will come in. We just know that each order is equally likely. And the goal is to select the best element, or the element with the highest weight. How do you quantify how good an algorithm performs? Because you can't really achieve the optimal always. So goodness is defined as competitive ratio, which is optimal over the expected value of the algorithm. So in this specific case, an e-competitive ratio has been achieved, and also it has been shown to be optimal, so we cannot do better than that. What does e-competitive means? It means that in expectation, we can get at least one e fraction of the optimal. So the algorithm is quite simple. It says that you first have a sampling phase. So for n over e elements, you don't select any element, and you just observe their weights. This is so that you get a feel of what the elements look like, what their weights look like. So let this be the set S. After this sampling phase, you will select the first element that has a weight bigger than any element in the sample. So I'm not going to analyze it here, but if you try out the analysis, you can see that the probability that you select the highest element is exactly 1 over e, which means that we have at least a e competitive ratio. Okay, so what are matroids? So the matroids themselves are a structure that generalize the notion of independence. So if you remember from linear algebra, a set of vectors are independent if neither of them can be a linear combination of the other. So that's what we call independence, and they have certain properties. So we just generalize that notion. What do we really mean by independent? So a matroid is just some ground set E and some independent sets I, where I has the following properties: that the empty set is independent, any independent set, its subset is also independent, and if you have two independent sets, where one of them is smaller and one of them is bigger, then there exists some element in the bigger set that you can put in the smaller set, and it will still be independent. So what does this really say? Well, intuitively it says that we are not doomed if we select a wrong element. Because if we select a wrong element, we know that, okay, we still have other elements that we can include in our set, and it would still be feasible. Okay, so these are matroids. The problem now becomes that we have n elements that are revealed in an online manner, similar to before. Now the algorithm must pick a set of elements such that the selected set is still independent. And of course, the goal is to maximize the sum of the weights of the chosen element. So in this specific problem, similar to the previous one, it has been conjectured that an e-competitive ratio also exists for this one. But this problem has been open for over a decade. So for general matroids, the best ratio that has been achieved to date is O log of k, where k is the rank, meaning the highest cardinality of the independent set. Better results have been shown for some specific classes of Matroids. So let me just give you a few examples to give you some sort of intuition. Uh, and these are in roughly list of being more generalized. So the last one is very general and the first one is quite specific. So we have the K uniform matroids, in which the elements are the ground set and any set of K elements are independent. So if you recall, the secretary problem is the same as the one uniform matroid, because any one element that you select is still feasible, is still doable, but you cannot select any more. We also have partition matroids. So the ground set are just again some elements and they are partitioned. And from each category, they're partitioned into categories. And from each category, you must select some, at most, some constraint number of elements. Okay, and both of these have been solved in e-competitive ratio. And then we have graphical matroids, which I think are the most intuitive one. So now we have edges that are the ground set, and a set is independent if the selected edges do not form a cycle. So I'll just give an example of that in a bit. The dual of that, we have co-graphic matroids. Again, edges are the ground set. Now independence is defined as follows. A set is independent if after removing the set from the graph, the number of connected components do not increase. So if the graph was already connected, we cannot select edges that collectively disconnected. We have binary matroids in which the elements are the columns of a 0-1 matrix. The set is independent if the columns are linearly independent. And of course, we have the normal generalization to it in which we allow not just 0-1 matrix but any matrix. So this is just linear matroids. So to just give you an example of what this problem looks like, assume we have this graph and we know exactly how many edges we'll receive. Let's say we'll receive eight edges. So we receive this edge 1 and let's say we choose not to pick it. Why would we not pick it? Well, maybe we receive something better. So in the next one we receive 3 and then we decide, okay, we'll take it. And then we receive a 4, we decide to take it. We receive a 5, we decide to take it. And then we receive a 1, we decide not to take it. We receive another 1, we decide not to take it. And then we receive a 10. Maybe we'll want to take it because it's a very high weight element, but we just cannot, because if we do take it, then we form a cycle, the 5, 4, 10 cycle, which means it's not feasible. So this is the optimal solution, or the optimum in hindsight is just the maximum spanning tree. We can see that this algorithm achieved, or rather this example achieved 12 units and the optimal is 20. So the competitive ratio in this case is 0.6. So to just sum it up, we went over what the normal secretary problem is, then what matroids are, and then naturally what matroid secretary means. We went over some examples. So next, Daniel will give a specific algorithm for graphic matroids that achieves a 2e competitive ratio. So that's all from my side. Let me know if there's any questions.
Okay, is there any questions for the speaker? Okay, cool. I can see your screen. You can get started.
Sure. Okay, hi everyone. I'm Daniel Ji Sin, and after Moment has defined the matroid secretary problem, I'm going to introduce a specific case, the graphic matroid, which is a matroid defined from graph and is relatively easy to understand. So let's get started. In this presentation, I will first define what is a graphic matroid again, and then as we don't have any new concrete results, I will talk about an existing solution for the graphic matroid secretary that is 2e competitive. We will go over the algorithm and discuss why it works, and finally draw our conclusion. So first let me define again what is a graphic matroid. A graphic matroid is defined from a graph. So we first have a graph G with vertex sets V and edge sets E. The ground elements in the matroid are the edges, and the independent set are the acyclic subgraphs. That is, the edges can be chosen if they do not form a cycle. Following this, the bases, that is the maximal independent sets, are the spanning forests. And in the matroid secretary setting, we have the graph, and the weight of the graph is revealed one by one in a uniform random order. When the edges arrive, we have to decide whether to accept it or to reject it, and which is an irrevocable decision. And our goal is to select the maximum spanning forest, which is the maximum weight independent set, or at least something close to it in terms of weight. And here comes the algorithm by Kola and Powell in 2009, which is 2e-Competitive. That means the expected value of its output is always at least 1 over 2e of the offline optimal. In this algorithm, we first give the vertices a total ordering. We number the vertex from 1 to n, and then we form two directed graphs. One by orienting the edges from high to low numbered vertex, and then the other by orienting the edges from low to high numbered vertex. Then we pick one from these two directed graphs, each with probability 1/2, and repartition the edges based on the vertex they leave. We run the classical secretary algorithm parallelly for each vertex. So we are trying to choose one edge leaving each vertex, and we do this for each vertex parallel. So let's look at an example. We have this graph with 5 vertices. We first need to give it a random ordering of the vertex from 1 to 5. So yeah, one ordering could be like this. And then we can form two graphs. So this is the one formed G0 with edges pointing from high to low numbered vertex. We have edges pointing from D to A and E, from E to ABC, from A to B and C, and from B to C. We can also note that as C has the smallest index 1, we don't have any edge pointing away from it. After this, we need to run the classical secretary algorithm parallelly for each vertex. So let's see what we got for each vertex. For vertex A, we have 2 edges leaving it. For vertex B, we have 1. And again, for vertex C, we don't have any edge because it has the smallest index 1. And for D, we have 2 edges. And finally, for E, we have 3 edges. And these are the edges considered for each vertex that when we try to choose the best one for each vertex by running the classical secretary algorithm. To maximize the probability of choosing the edge with heaviest weights leaving each vertex, we sample 1 over e of the edges for each vertex and choose the next one that is better than all of those in the sample, which is just the classical secretary algorithm. Then we have a 1 over e probability of choosing the heaviest edge leaving each vertex by standard results. Now let's see why this works. And there are 2 parts: that it always gives a feasible solution, that is a forest, it doesn't contain any cycle, and that's the forest it gives has weight at least 1 over 2e of the offline optimal in expected sets. Now let's first look at the feasibility. We can observe that after giving a total order to the vertices and orienting the edges from high to low number vertex or the other way, from low to high number vertex, a directed acyclic graph is always given. If there is no cycle in the original graph, then of course the directed graph does not have any cycle. But if there is, you can easily prove by contradiction that we cannot have an order that gives a directed cycle. Otherwise, you will have a vertex number being strictly greater than itself. So we got a deck. And by selecting at most one going edge from a deck, we are guaranteed to pick the forest, even after removing the orientation. Again, we can easily show that if it contains a cycle, then more than one edge has been picked for some vertex, as the lowest number vertex in the cycle cannot have any edge, which means that some other vertex in the cycle has to take more than one edge. So we are guaranteed to pick an acyclic graph, which is a feasible set for the secretary problem. Next, we also want to show the competitive ratio, that it always gives at least 1 over 2e of the offline optimal in expected sets. First, we can orient the edges in the offline optimal from the leaves to the parents, and so on. Then we have an orientation for each edge, which is either the one in G0 or G1. Then for each vertex, we either have that edge in G0 or in G1, that is the 2 graphs formed by orienting the edges from high to low number or from low to high number. And the heaviest edge for each vertex is certainly heavier than that. And therefore, the sum of the heaviest edge leaving each vertex in G0 and G1, the total sum must be heavier than the weight of the offline optimal. Next, since we picked the heaviest edge with probability 1 over e from standard results from the secretary algorithm, and we choose G0 and G1 each with probability 1/2, we have the inequality here that shows that the expected value of the algorithm output is at least 1 over 2e of the offline optimal. So we have a 2e competitive algorithm. And finally, let's draw our conclusion. We have shown a 2e competitive algorithm for the graphic matrix secretary, and actually later work improved the competitive ratio to 4. And while the general conjecture that there exists a constant competitive algorithm for all matroids is still open, substantial progress has been made for different matroid, especially for matroid with special structure that we can exploit, just like the graphic matroid that we can exploit the structure of the graph. And here are some examples that Momi has also shown. Some work has been done using a technique called a forbidden set, and these are the results that they got. For graphic matroid, they improved it to 4, and we also have some other well-known classes like transversal matroid, laminar matroid, uniform matroid, regular matroid, etc. And another case that is interesting is the k-sparse matroid, which means the matroid that can be represented using a matrix, and at the same time, and the elements at the columns independence defined as linear independence. So we're trying to choose linearly independent columns in the matrix, and the columns arrive one by one in a uniform random order. And k-sparse here means that each column has at most k non-zero entries. We can note that this is actually a generalization of graphic matroid, as graphic matroid can be represented by the adjacency matrix, and the linear and the independence can be formed by the linear independence of the columns in the adjacency matrix. And we have at most 2 non-zero entries per column for the adjacency matrix for a graph, and is two sparse matroid. So it also fits into this representation of a k-sparse matroid. And the problem is that whether we can generalize such results of specific matroids to all matroids. The current best known algorithm for the general matroid, as Momin has mentioned, gives a log rank competitive ratio. While we are not that ambitious that we could beat it, we are still working on algorithms for specific cases in terms of the matroid and also variance of the problem setting. Some known results include that if the weights are assigned randomly instead of adversarially, we have a constant algorithm. And other variants we are looking at include if we have a look-ahead time frame, that is, we delay the decision of accepting or rejecting a certain element after seeing some more elements, instead of in the original setting that we must decide before the next element arrives. And also another variant that the independent constraint can be violated with some cost, and hope to give some positive results in these cases. And of course, ideally, a constant competitive algorithm could be given to the original matroid secretary problem for all matroids, but that's probably too much for us. And that's all I want to share. Thank you, and the floor is now open for questions.
Thank you for sharing. Is there any questions for this speaker? If not, we're gonna move on to the last